section 3.4 was rates of change in the natural and social sciences. So in the first half of this lesson, we looked at how the derivative or rate of change might apply to physics. Like we looked at particle motion, velocity, when the particle is at rest, when it's moving forward and backwards, diagramming the motion of the particle, finding the total distance the particle travels, that type of thing. We also talked about linear density, and we talked about current, and then we moved to chemistry. And in chemistry, we talked about instantaneous rates of reaction and isothermal compressibility. And then over on page 163, we want to start looking today at some applications to biology. Now, we could go through and we could use derivative to help us estimate the instantaneous rate of growth of all kinds of things. Like we could talk about the rate of growth of a particular bacteria at this particular instant and how it responds to the introduction of an antibiotic or something like that. We could use it for population of a community or of a country or that type of thing as well. Over on page 164, they give us another application to biology, and that is called laminar flow. Now, they go through here and they give us a great deal of groundwork so that we understand what we're talking about. In example 7, it says, when we consider the flow of blood through a blood vessel, such as like a vein or an artery, we're going to take the shape of that blood vessel to be a cylindrical tube with a radius of capital R and a length of L. So radius, capital R of the cylinder itself, and L, the length of that cylinder. Because of friction at the walls of the tube, the velocity V of the blood is going to be greatest right down the center, right? You could think of that as like a central axis. There's nothing inhibiting the flow of that blood right through the center, so it's going to be quickest there. But as you move closer to the wall of that vein or artery, even if there's not any kind of blockage or anything there or any kind of a buildup, even the friction from the edge of the wall would cause that blood to slow down and run slower along the edges than it does through the center. So there is going to be a rate of change of the velocity of the blood flow in relation to how far it is from the center of that vein or artery. So it says, because of friction at the walls of the tube, the velocity V of the blood is greatest along the central axis of the tube and decreases as the distance lowercase r from that central axis increases until that velocity would become 0 at the actual wall of the vein or artery itself. And that is called the law of laminar flow. And so they give me the law of laminar flow here in our textbook on page 164, and I also put it there in your notes for you. So in this formula, they go through and they define a few more components there. This little guy right here that kind of looks like a fancy N, that is eta. It's the lowercase h in the Greek alphabet, like we have alpha, beta, theta. This is eta, lowercase h in the Greek alphabet. And in this case, eta is representing the viscosity of the blood. Capital P is the pressure difference between the ends of the tube. P and L are constant values, and the velocity is a function of the lowercase r, which is that varying radius as to how far I am from that central axis as I'm approaching that wall of the tube. And so the average rate of change of the velocity as we move from that central axis outward, that would be our lowercase r, we could find then the rate of change of the velocity with respect to how far away my radius away from that central axis. So if we wanted to find that rate of change, that is called velocity gradient, and it's literally just a derivative. So like on the AP exam, they wouldn't go through all of that detailed discussion, but they might give you just a real quick little synopsis of what you're working with. They would give you the equation for laminar flow, and they would ask you to find the rate of change of the velocity with respect to the lowercase r radius. And that would be our velocity gradient. So we should be able to apply calculus to that formula. Now, a couple of things that they've told me. they've told me that all of the components out in this number are all constants. So it's as if I've got like a 5 sitting here. So we have a constant rule for derivatives that says if you're taking the derivative of a constant times something, you can just pull that constant out in front and ignore it and take the derivative of your function and then bring that constant back in, right? So that's what I'm going to do. I'm just going to ignore this guy. I'm going to bring him out in front and I'm going to focus on the derivative of my function. Now, capital R is a constant because it is literally the radius of the vein or the artery. It's not changing. But lowercase r was the distance that we were away from that central axis, and that was a changing quantity. So when I take the derivative of a constant, I get 0. When I take the derivative of a variable, r squared, I'm going to get 2r. So I would have this guy times negative 2r. So that would give me negative 2rp over 4 eta L, and I could reduce the 2 over 4 down to 1/2. So I've created the rate of change. I've created the velocity gradient formula. All right, then they asked me to go back and to find the laminar flow and the velocity gradient given some particular dimensions. So they've told me that the pressure is going to be 4,000. That eta is going to be 0.027, that L is going to be 2, that capital R is going to be 0.008. Now, if they only gave me that, I would be able to throw this into my calculator to get the constant 18,500, and that would kind of give me a formula that I could use for laminar flow, so that if we wanted to go through and change that radius, that distance away from the central axis over and over and over again, I could still use this same formula. They asked me to find the laminar flow at the particular point when the radius is 0.002. So I can go back and put 0.002 in for that lowercase radius, and I can find my laminar flow at that particular radius away from the central axis. I also can find my velocity gradient there, because again, I'm going to plug in that 0.002 for R, that same 4,000 they had given me for P, the same eta value and length value, and I can find my velocity gradient as well. So again, being able to take a formula that I've never seen before in a scenario I'm not familiar with and just apply calculus to it. So on the test, I would give you this formula for laminar flow, and I would ask you to find the velocity gradient. So you would need to be able to derive the velocity gradient formula, and then we could also calculate, you know, particular values based on radius and pressure and eta and L and that type of thing. Over on page 165, we have some applications to economics. And they're actually going to start a discussion here in section 3.4 that we will continue and build on later on. So we will see these economic applications again. But over on page 165, we talk about applications to economics. Now, if you are Sony and you are starting up a new manufacturing plant to produce television sets, if you make 100 television sets at that new plant, they might cost you $1 million each to make. And you're surely not selling them for that, right? Because you've got to pay all your startup costs, you got to buy all the equipment, you got to hire all the people, you got to pay the mortgage. I mean, there's so much to take into consideration that the price of each of those TVs, if you're making a small number of them, is going to be extremely high. But once you get all that up and running and you're making a ton of them, maybe, you know, by the time you make 5 million of them in 1 week, they might only be costing you $100 each to make now, and you're selling them for $1,000, and now you're in business, right? So there's going to be a rate of change of the cost for making one TV set depending on how many of them you're making. If you're only making 50 of them, they cost a whole lot more than if you're making 5 million of them, right? So the cost per television set is going to depend on the number of sets you're making. And that's exactly what we're looking at in example number 8 when they talk to us about if you have capital C of X as a total cost that a company incurs in producing X units of a certain commodity, in our scenario, television sets, then that function, capital C, is called the cost function. If if you wanted to find the rate of change of that cost with respect to the number of units that you're making, like we were just discussing, then that would be the derivative of your cost function, and we call that the marginal cost. In calculus, anytime you see the word marginal, it's going to mean derivative. We'll see marginal cost, marginal revenue, marginal profit later on when we're working on this. There are people that go in and do something called a marginal analysis for a company where they tell it, this is your break-even point, this is how to maximize your profit, this is how to minimize your cost, and we'll be looking at some of that later on when we build on this topic. But for right now, the word marginal means derivative. So if they give me the cost equation, which they will have to give me the cost equation, and they say find the marginal cost, all I'm going to do is take the derivative of that. So we could go through here and say the derivative of a constant is 0, the derivative of 5x is 5, and the derivative of 1/100th x squared would be 200th x. So there's our marginal cost formula, right? Then they say, what's the marginal cost if I'm producing exactly 500 television sets? So we're saying, what's the rate of change of the cost with respect to the number of units that I'm producing if I'm producing 500 of them? So I could go through and I could just plug 500 into that marginal cost formula that we just created. And if I plug in 500, I find out that the cost is changing at a rate of 15 when I'm making 500. So that gives me a good idea of what the cost for one would be when I'm making 500. Here's another way that I could approximate the cost for one at that production level. The next thing that they ask me to do is they ask me to find the actual cost of the 501st item. Now, if I wanted to find the actual cost of the 501st item, I could find the cost of making 501 of them and subtract off the cost of making 500 of them, and that would just leave me with the cost of that one item, right? That goes back to the cost equation, right? Not the marginal cost equation. So I could go back and I could say, okay, let's plug 501 into my cost equation and plug 500 into my cost equation. We're obviously doing that with our calculator, not by hand. And we would get $15.01. So you'll notice that the marginal cost at that production level and the actual cost of making one unit at approximately that same place, those two should be maybe not exactly equal to each other, but they should be a good approximation of each other. And so you'll notice I got $15 here and I got $15.01 here. If I got $15 for one of them and $1,000 for the other, something's wrong. And there's sometimes that finding one of these is much easier than finding the other. Not necessarily in our example here, but in a real world situation, it might be much easier to find the marginal cost than it would be to find the actual cost of one item, or vice versa. And so it's nice to have two ways that we can do that. All right, so here is our homework for tonight on pages 167 and 168, just doing a couple of these.